Okay, today's video is over improper integrals with one infinite bound. Now, an improper integral is an integral in which the boundaries consist of an infinite bound, multiple infinite bounds, or a point at which your integrand would have a asymptote, vertical asymptote. And so I'll make videos on the other two at a future date. But for now, we're just going to stick with improper integrals with one infinite bound as an introductory topic. So to be concise, an improper integral is just an integral in which you can't solve it in its current state. So take this over here, the integral from a, which is just a constant, to infinity of f of x. Now, normally we couldn't solve this. We can't just say that this is equal to f of infinity minus f of a, f of x, capital F of x being the integral of f of x. We can't do that for some reason. And so we have to take the limit as n approaches infinity of the integral from a to n of f of x. And it's incredibly simple, really. That's all you have to do. And so we might as well jump into the practice problems. Okay, this is practice problem 1. We need to find the integral from 1 to infinity of 6 over 1 plus nx, or 9x squared dx. And since this integral features a boundary consisting of infinity, the upper boundary here, we can tell that this is an improper integral, and as such, we're going to have to reorder it. You can say that it is equal to the limit as n approaches infinity of the integral from 1 to n, 6 over 1 plus 9x squared dx. And so now we just have to integrate. One thing worth pointing out is that our integrand here, 6 over 1 plus nx squared, almost looks like the derivative of arctan. Now I'll put the derivative of arctan down here just for a moment. We can see that the derivative of arctan is equal to 1 over 1 plus x squared. And so if we can somehow get this, get our integrand to look like the derivative of arctan x, we can simply integrate and end up with arctan x, or arctan whatever. So we're going to begin by reordering this once again. We can say that this is equal to the limit as n approaches infinity of 1 to n, 6 over 1 plus 3x squared. And so all I did was manipulate this because, of course, 9x squared is equal to 3x squared. And so that means that our 3x is very clearly our x of arctan. And so we're going to begin by assigning, let me write this down here in red. We're going to begin by assigning u to 3x. And I'm simply just exercising u sub at this point. I've made a video on u sub in the past, so if you're confused, you should probably watch that. But we end up with du is equal to 3 dx. And I forgot to put dx up here. That's fine. I'm going to erase this now. Hopefully you're aware of your arc trig identities. And so all we have to do now is substitute. So we can say that this is equal to the limit as n approaches infinity of 1 to n, 6 over 1 plus u squared dx. However, let me reorganize this a bit. 1 plus u squared dx. However, we have a variable in our integrand u, however, we're differentiating with respect to x as shown by this dx. And so we need to get rid of our dx. We can do so by substituting our du in for dx. However, we're going to have to manipulate this quite a bit. We're going to say that 2 du is equal to 6 dx. And this is because we have a 6 dx in our integrand. And so from here, we can substitute 2 du in for 6 dx. We end up with the limit as n approaches infinity, the integral from 1 to n, 2, 1 plus u squared du. I'm going to erase this over here. It's quite clear what our integral is. It is, give me a moment, I'll write this in pink. It is the limit as n approaches infinity 2 arctan u from the boundaries 1 to n. However, we have u in our function, 2 arctan u, and if we recall, u is equal to 3x, and so I'm going to erase u and replace it with 3x. And this is essentially our integral. However, we still have yet to solve it. We can say that this is equal to the limit as n approaches infinity of 2 arctan 3n minus 2 arctan 3 times 1, which in this case is just going to be 3. In every case, it's going to be 3. Now, I don't actually know the value of 2 arctan 3, so I'll keep it in that form. However, I do know the limit as n approaches infinity of 2 arctan 3 times infinity. Now, this piece of knowledge you're just going to have to learn. The limit as n approaches infinity of arctan infinity is, I believe, pi over n. You should probably know just the limit as n approaches infinity of all your arbitrary functions. However, this one specifically is quite important. And I'll write our final answer up here as I'm running out of space. But essentially, we have the limit as n approaches infinity of 2 arctan 3n. Essentially, I got to stop saying that. What we're really doing is we're just replacing n with infinity. Mathematically, that's not exactly what's going on, but for all practical reasons, it is. And so we can say that this is equal to 2 arctan 3 times infinity, which is infinity, as you know, minus 2 arctan 3. And the reason the second term doesn't change, 2 arctan 3, is because there's no n. It really isn't affected at all by the limit. But as I said, arctan infinity is equal to pi over 2, and so we end up with 2 times pi over 2, which is pi, minus 2 arctan 3. And as I said, I don't know the value of 2 arctan 3. But this is our final answer. This is the integral from 1 to infinity of 6 over 1 plus 9x squared dx. Okay, this is practice problem 2. Told to find the integral from negative infinity to 5 of e to the power of x. Hopefully you'll be able to identify this as an improper integral. And yes, the same process that applies to positive infinity applies to negative infinity. And so we can say that this is equal to the limit as n approaches negative infinity of 5n e to the power of x. Now, the antiderivative of e to the power of x is e to the power of x. So we end up with the limit as n approaches infinity of e to the power of x from n to 5. And so we can begin substituting our boundaries in, and we end up with the limit as n approaches negative infinity of e to the power of 5 minus e to the power of n. And so from here, we can take the limit. We can say that this over here is equal to e to the power of 5 minus e to the power of negative infinity. Now, e to the power of negative infinity, or rather, e to the power of any negative exponent can be represented by 1 over e to the power of that exponent. Now, keep in mind that this is not a proper way to represent the limit as n approaches negative infinity. However, it is a good interpretation, if that makes any sense. Like this mathematically isn't correct, but it's a good way to understand what's going on. And so really we can say that this is equal to e to the power, e to the power of 5 minus 1 over e to the power of infinity. Now, e to the power of infinity is infinity. And so 1 over e to the power of infinity is equal to 1 over infinity. And 1 over infinity is equal to 0. And so what we have over here is really e to the power of 5 minus 0, which, as you know, is e to the power of 5. And so that is the integral from negative infinity to 5 of e to the power of x. Okay, this is practice problem 3, the final practice problem for today's lesson. We're told to find the integral from 3 to infinity of 5 over x. And so we'll say that this is actually equal to the limit as n approaches infinity of 3 to n 5 over x. Let's begin by taking the integral the antiderivative of 5 over x. I'll draw it down here in a separate color. The integral of 5 over x is equal to, as you may imagine, 5 natural log x. And this is just because of the properties of natural log make it so that natural log f over x, when derived, is equal to f prime x over f of x. And so the same applies, oh god, hold on. And so the same applies over here. If we were to take the derivative of 5 natural log x, we'd end up with 5 times x times the derivative of x, which is 1, over x. And so that's how we end up with an answer of 5 natural log x. That's just a refresher on one of the properties of integration. And so if I were to go back up here to our original equation, I can say that this is equal to the limit as n approaches infinity, 5 natural log x from 3 to n. And so we can begin substituting in n, and we can begin substituting in 3. So we can say that this is equal to, 1 second, let me erase this. We can say that our equation so far is equal to the limit as n approaches infinity of 5 natural log n minus 5 natural log 3. And we can take the limit of this entire argument. Really, we only need to take the limit of the first term, as that's the only one that would be affected, as it's the only term with n. So we can say that this is equal to 5 natural log infinity. Again, not really a proper way to write this mathematically, but it's a good representation, minus 5 natural log 3. Now, the issue here is that 5 natural log infinity, or really just natural log infinity, is equal to infinity. So we end up with 5 times infinity minus 5 natural log 3. I'm going to keep saying this. This is not a proper representation of the limit as n approaches infinity of 5 natural log n, but it's how I'm going to write it for the time being, so you all understand it. Now, this here is equal to infinity. So, yeah, this improper integral, as you can imagine, does not have a definite value. So this is what's known as a divergent integral, in the sense that it does not converge to a specific value, as you can see, because it's equal to infinity. But that's today's lessons. That's our introduction into improper integrals. I'll make 2 more videos following this one. If you have any suggestions for future videos, please put them in the comments below. Thank you.